Hey everyone, Mr. Allen here. We're going to start on identities now. Identities are equality relations which are always true for all values in the domain. Don't want to confuse that with what we've known before, equations, where we are often solving for the answer. There's a certain value of x that makes this side, the left side of the equation, equal to the right side. In the case of a quadratic, there might be a couple of answers. There can be zero answers, of course, as well. In identity, we're talking about every single legitimate x value will always make the identities true. So we've seen a couple of them already, specifically the reciprocals you've used in the past. Sine of any angle is always going to give me the exact same answer as 1 over cosine of that angle. The definition of cosine is the reciprocal of sine. There are a couple more that we'll look at today. You'll see a bunch more over the course of however many days we're working on this. These are the key ones, and we may just stick with using them. I'll sort of see how I feel later on. So what we'll be doing today is using these facts to simplify expressions. So simplifying expressions with identities. So given the information we saw on the first page, I know that tan is equivalent to sine over cos. And so if I'm given this simple expression, I can simplify it further, potentially at least, by substituting in sine over cos for the value of tan, divided by cos. And then, of course, I have a straightforward multiplication here. Cos times sine divided by cos. Cos then divided by cos gives me the value 1, and of course that means that sine x is my final simplified expression. So this expression here is exactly the same as sine x, and obviously a slightly simpler form. Continuing on then, same sort of thing over here, tan squared over secant squared. What I'm interested in doing is simplifying this by doing some sort of substitution that will get me to potentially at least simplify. Right now, tan over secant doesn't help me any, but tan we know is sine over cos. And actually, I'm going to write it this way. Secant we know is 1 over cos. And so secant squared is 1 over cos squared. I'm writing it this way to avoid having a stacked set of fractions, or rationals inside of rationals. And because, of course, it allows me to simplify a little bit further here. If I'm dividing by a fraction, we multiply by the reciprocal. And yes, the reciprocal is secant, but I don't want to do that. What I'm looking to do is simplify again. So I'm going to rewrite this as cos squared over 1. And then, as we did last time, when we try to multiply this through, we get a cos multiplying by cos squared and dividing by cos squared, which then gives me a final solution of, once again, simply sine squared. Down here, again, I'm going to stick with these basic, I lost them now. I'm going to stick with these basic fundamental identities, at least initially. And so I have tan squared plus 1. The tan squared specifically I know to be sine over cos, or sine squared over cos squared, excuse me. I know tan to be sine over cos. So I will rewrite my expression this way. Now, at least initially, this doesn't look like much of an improvement. It certainly doesn't look simplified versus the original. But I'm going to continue. In my denominator here, I can simplify this by creating a single fraction. To do that, I need a common denominator in my existing denominator. I know, scary, right? So the common denominator will be cos squared. Ooh, sorry about that. Cos squared x, cos squared x. And now with the common denominator here, I can make that into a single fraction. And I'll have sine squared x plus cos squared x as the numerator in my denominator over cos squared x. And I'm almost done now. Sine squared x plus cos squared x was the, keep doing that, was the Pythagorean identity. So it's the same as just the value 1. And so now I have 1 divided by 1 divided by cos squared x and so finally I have 1 divided by, again, 1 divided by cos squared x. If I multiply by the reciprocal, I get 1 times cos squared x, or of course simply cos squared x. Now, I made that look a little longer than it needed to. As you get used to this, you'll sort of see that and recognize pretty much that you can jump right to this point. It turns out that the denominator of the denominator, when we multiply by the reciprocal, the denominator of the denominator ends up multiplying by the numerator. And you'll sort of start to recognize that. I have to flip this and multiply, and so this will be multiplied up top, and obviously I can get to this in a single step. A couple more here, I'll go through them fairly quickly. Cosecant is equivalent to 1 over sine. Tan is sine theta over cos theta. Secant is 1 over cos. Now, again, a couple of things. The first thing I would notice is I'm going from secant, which is sort of in a nice form, to the reciprocal 1 over cos, which essentially is bringing me in a fraction. And for the most part, people won't maybe like that initially. But where we're leading to, we want to have kind of a standard of using sines and coses whenever possible. Eventually, I'm going to be looking to make this equal to a very specific simplified expression, not just a simplified expression. And if I sort of have a standard of always using sines and coses, that will be kind of a nice way to go. At least sort of until I get to the end of the question. So here again, 1 times sine, sine times cos, and I'm dividing. So sine divided by sine leaves me 1 over cos plus 1 over cos theta. That was a theta, which is 2 over cos theta. And of course, 1 over cos theta is secant. Maybe that would have been the smarter thing to do, is change this to secant and secant right away. Either way, I have 2 secant thetas. Okay, so you can sort of see even there, if right away you had noticed that was secant, I could have left this as secant initially and gone to 2 secants. Both are perfectly correct. Okay, so last couple here, I want to just sort of introduce the idea that that sine x and cos x and tan and so on are all just variables like any other you've used previously. If this were something that looked a little different, maybe y squared, z squared minus y squared, your first instinct would probably be to factor. There's a common factor of y squared, and so that would be y squared is z squared minus 1, and then continue from there if you can. The same is going to hold now with sine squareds and cosquareds. This is some value that I don't know. Depending on the value of x, of course, it changes. It doesn't change the fact, though, that it's an unknown value squared with more unknown values squared minus an unknown value squared. So I'm going to factor out the sine squared x. This will leave me with cos squared x minus 1. And I know that negative 1, or well, the 1 specifically, is sine squared plus cos squared, and so at this point I might want to consider doing something with that. I could put in sine squared plus cos squared. Let's just see where that leads us. And if I do try to expand this and simplify, I get sine squared x. Cos squared minus cos squared is 0, and then I get negative. So cos squared minus cos squared minus sine squared, I get minus sine squared. And so sine squared times sine squared is negative sine to the fourth. Now, I'll be honest, I didn't know how well that was going to work, but it's just sort of something that it's one of the rules I have. I know that cos squared and sine squared add to 1, and so when I see a cos squared there and I see a 1, it seems like a reasonable thing to try, substituting the cos squared plus sine squared and just seeing what's going to happen. Obviously, the fact that it was a subtraction, I could kind of see that I was going to get cos squared minus cos squared, but it was still sort of a little bit of a try there and see what happens. Okay, last one. My first instinct when I look at this is I sort of notice that I have sines and coses already. I don't really have maybe anywhere to go, at least initially. The one thing I do sort of think that it's too bad this wasn't a cos squared, because at least then I'd have just cos in the question. And so what I'm going to use is the Pythagorean identity kind of rearranged here to substitute for sine squared. And again, really what I'm doing is I'm trying to see what's going to happen. This is essentially a puzzle now. And I'm thinking one of the things I can do, maybe the only thing I can think to do right now, is see if I can get a cos squared in here instead. And so since sine squared plus cos squared is equal to 1, 1 minus cos squared is equal to sine. Okay, so just the Pythagorean identity rearranged gives me at least a chance to get just cos in the question. Now, really, whether it's going to help, again, initially I don't know. But it's the only thing I can think to do here is just try to get coses in the question. So just in case that wasn't clear, 1 is equal to sine squared plus cos squared. Subtract the cos squared from both sides, and we end up with 1 minus cos squared is equal to sine squared. Now, finishing up. So what happens here? I can do a little bit of math. Obviously, I have 1 plus 3 is 4. 4 minus cos squared is now my numerator, over 2 minus cos. And hopefully when I look at this, I recognize it as a difference of squares. And so In the same way that 4 minus y squared, I could do a difference of squares. Here I can do a difference of squares, and it's 2 minus cos and 2 plus cos. That's how difference of squares works, divided by the 2 minus cos, and you can see, last step, this and this divide, and my simplified expression is now 2 plus cos x. Okay, so stopping there. We'll be spending a few days on these, so don't panic if there's anything there that sort of seems confusing. Some of it is trial and error, and then a lot of it is experience. As you get experienced, you'll start to see patterns that emerge, things like this. Well, sine squared can be 1 minus cos squared, and I sort of saw that there was a subtraction in the denominator, and I knew that there was potential for some sort of a difference of squares on top. And so you kind of, in some cases you're just attempting it and seeing what happens. Okay, signing off for now.